Welcome to ECE 165. This is lecture 9, where we will get to discuss components of energy and power in digital CMOS circuits. So this is a new section header here, so let's go ahead and indicate that. We're talking about energy and power. So this is section header, so let's go ahead and double box this. Okay. If you are following along in the West Harris book, that would be chapter 5 in West and Harris, or section 5.5 in Rabbi Chandrakasan and Nikolic book. Okay, so before we get into talking about how to model energy and power in digital circuits, let's go over some definitions, just to make sure we're all on the same page in terms of what we're talking about here. Definition number 1 is instantaneous power. So hopefully the meaning of this is fairly precise, where it means the power that is instantaneously consumed at time t in a given circuit. This can be given by P of t is equal to, in a digital circuit, we have the same supply voltage everywhere, so we can just measure the current from that supply. We'll call this IDD of t times VDD. Okay, so let me just make an explicit note here. So IDD is the current drawn from VDD. So that is what we call the instantaneous power consumption. Now, we also have energy. And it's very important when we're dealing with digital circuits to clearly distinguish between power consumption and energy. It's not the same thing. A lot of people tend to use the words interchangeably, but they are not interchangeable. They mean different things. So energy is consumed over an interval, usually indicated by t. So we say that the energy consumed over interval t is equal to the integration of 0 to t of the instantaneous power P of t dt. Okay, so we integrate all the power over a unit t, and that gives us our total energy. Now we can also specify something called average power. And the best way to define average power, P average, is just to take the energy in some time cycle and divide it by that time cycle. Or in other words, it's just the average of the power consumption in that time cycle. Okay, so it's very important to make sure that we clearly understand the differences between these various definitions. So in digital circuits, we of course have instantaneous power, energy consumed, and average power consumed over a specific time period. That's the same in analog circuits and any other kind of circuit. In digital circuits, we have several distinct components that we'd like to zoom in on because digital circuits consume power in a slightly different way than perhaps you're used to if you're an analog circuit designer. So let's go over these components of energy and power in digital circuits. So the first one, and probably the main one that we're going to deal with, is what we call dynamic or switching energy. And what we mean by this is energy that is consumed due to the process of charging and discharging capacitance. This could be gate capacitance, drain capacitance, parasitic wiring capacitance, capacitance that exists anywhere in our circuit. When we go from a logic 0 to a logic 1, we will charge or discharge parasitic capacitance, and that causes some degree of energy consumption. Another component of energy and power is short circuit power. Okay, sometimes called direct path power consumption. And this manifests by as the second name implies, a direct path between supply rails during switching. So remember, when we have our inverter and we're switching from a logic 1 to a logic 0, for example, what ends up happening is there's a part in that voltage transfer curve where both of the transistors are on and they're saturated, assuming VDD is larger than the threshold voltage and we're not operating fully in the sub-threshold regime. So at this point in time, we have effectively a direct path between VDD and ground. So we call this short circuit power. There's another type of power consumption that we've already spent a little bit of time computing. It is called leakage power. So as the name implies, the circuits are just sitting there, not necessarily doing any computation, but there's current that's leaking through your devices. So this could be sub-threshold. I'll write this as sub-VT, but in my mind I'm saying sub-threshold. This could be due to reverse bias diode leakage, which we've modeled. Could be due to gate leakage, and so on. Now, for the purposes of this course and for the purposes of most practical designs, we are usually limited by sub-threshold current, not these other two, but you have to make sure that you model all of this correctly when making that determination. And last but not least, we sometimes in digital circuits actually do have static power consumption. Now, we haven't seen a case necessarily where we would have that in a static complementary CMOS circuit, but we certainly have seen it in, for example, NMOS logic or pseudo-NMOS logic. So this would be, for example, when we have current sources in blocks we call sense amplifiers. So even though we're building digital circuits, we actually do sometimes have to build amplifiers. This is particularly used when we build memory arrays like SRAM circuits or DRAM circuits, for example. We'll get into that later on in this course. Or if we have things like NMOS logic or pseudo-NMOS logic where we have direct paths to ground, some forms of ratioed logic, etc., have the possibility of having actual static bias currents when the output of said logic gate is in one of the two states. So these are our main components of energy and power in digital circuits. What we're going to predominantly focus our attention on is dynamic or switching energy, as well as leakage power. It turns out that these are usually the two most important pieces of power in modern digital circuits. So I want to spend most of the time of this lecture discussing arguably the most important component of power and energy in digital circuits, and that is switching energy. Okay, this is usually the dominant power consumer or energy consumer of a digital circuit. So when deriving where switching energy comes from, I'm going to be very slow and explicit, simply because this is a very important concept and it's fundamental to the way that we typically operate digital circuits. It's not fundamental from a bigger perspective of charging and discharging capacitors, but it is fundamental in terms of how we typically build digital circuits. Now, we see this everywhere. Anywhere we're charging or discharging a capacitor, you'll see something like this happen. So obviously this happens all the time in digital circuits, but it also does happen in RF circuits and analog circuits and so on. And it's remarkable how many times I see very smart, very experienced designers not truly fully get this. Okay, so I want everyone who's listening to pay very careful attention and make sure that you really understand what we're talking about here and understand it at a very deep and intuitive level. Okay, so to do this, what I'd like to do is go over a simple example. Consider the following circuit. All right, so we have a voltage source. It is connected through a resistor to a capacitor. Very simple circuit. Okay, let's call this resistor here R. Actually, let me, just for clarity here, use a different color. This is R. This is C. And this node here is V out. And V in is a voltage that starts at 0 and then switches to VDD. So we start at 0 and then we switch to VDD. All right, so let's think about intuitively what happens here. At time t equals 0, when V in is equal to 0, V out is also equal to 0, right? So we can go ahead and draw that plot. So let's go ahead and do that here. All right, so we're plotting V out of t versus t. All right, so at time t equals 0, when V in is still, or perhaps t equals 0 minus, when V in is still 0, V out is definitely 0, right? Now, as soon as V in goes to VDD, then what's going to happen? We're going to charge V out until it reaches VDD, right? We know how this circuit operates, right? So it'll look something like this. It'll have some exponential charging function, and then it'll plateau off where it hits the value of VDD. And the function for this, so V out for time t is greater than 0 plus after that step function has happened, is equal to VDD times 1 minus e to the minus t over RC. Okay, so this is an exponential function that increases until it plateaus at VDD. So this we all know. This is the basics of Elmore delay and so on. So we've studied this, we know about this. Now, what I'd like to be very explicit about is what is happening to the current in the circuit while this is happening. So once VDD reaches, once V in reaches VDD, then we say we have a current that's flowing through this circuit, I of t. This current is the one that's charging the capacitor to the output, right? So we can say that this current, I of t, is equal to what? Well, once V in is at VDD, then the current we can actually say is the voltage across the resistor divided by the resistance. So the voltage across the resistor is VDD minus V out of t, divided by R, right? That's the current. Now, we already derived the function for VDD, so we can just substitute that in here, and what we get is VDD over R times e to the minus t over RC. All right, so what we can do now is we can now go ahead and plot that current response over the same time period. Again, I'm being very slow and explicit here, and I'm doing this intentionally to make sure that we're all on the same page here. So this is I of t. So what does I of t look like at time t equals 0? At time t equals 0, 0 plus I should say, the voltage on the capacitor cannot change instantaneously. And instantaneously, we then have a large voltage across the resistor, and so therefore we have a rather large current. It's VDD over R, right? So we start here at VDD over R, and then we decay down exponentially. Right? So again, I've been very explicit here. This is not rocket science. These are simple first order RC circuits. What is going on here? Well, let's go ahead and now compute the total power dissipated, or rather the instantaneous power dissipated in this circuit. P of t is equal to, well, there's a number of different ways we can do this, but we know that the power dissipated in an RC circuit must be dissipated in the R element. This is equal to I squared of T times R. Okay, so we have an expression for I of T, so we can go ahead and substitute that in. That's VDD squared over R squared times e to the minus 2t over RC times R. Okay, so that's the instantaneous power dissipated in the circuit. What we can then now do is compute the energy dissipated in the circuit over some time. Now specifically, I want to compute this over infinite time. So I'm going to integrate from 0 to infinity p of t dt. All right, hopefully this doesn't result in an infinite value. So we can go ahead and do that integral. We pull out the VDD squared, we pull out the R squared out of the integration. Integral from 0 to infinity, e to the minus 2t over RC. And sorry, actually that shouldn't be an R squared, that's just R because it cancels with the other R in the numerator, dt. Okay, so that's equal to VDD squared over R. Integral is minus RC over 2 times e to the minus 2t over RC, evaluated between 0 and infinity. Okay, so if you do this evaluation, what you'll get is a somewhat surprising result, or perhaps it's surprising if you haven't thought about this very deeply. So the result is that of this integral is that the energy dissipated in this resistor is equal to 1/2 C VDD squared. That's it. All right, so this is a very, very important result. It's so important that I'm going to box it. And then I'm going to put not 1, not 2, but 3 underlines here. Okay, that's how important this is. So why is this important? What is going on here that we care so deeply about? Well, the most important thing here is that the energy dissipated to charge a capacitor is independent of the value of the resistance. Okay, so we said that the energy being dissipated in the circuit is dissipated on the resistor, and yet the value of said resistor seems to not matter. That's a bit of a surprising result. We would think that because the energy is being dissipated on the resistor, that the value of the resistor should matter in the amount of energy that is being dissipated. It turns out that that is not the case. And this is really, really important for everybody to understand. That's why I boxed it and then underlined it 3 times. Okay, very, very important to understand. In fact, I'm going to put a couple stars here as well to extra emphasize the importance here. So the energy to charge a capacitor is equal to 1/2 CV squared, where V is the voltage on that capacitor. The reason for this is actually very intuitive. All right, if we have a very small resistance, R is very close to 0, for example, then what's going to happen is that the RC time constant of the circuit is very fast. So it will charge up very quickly. But as a result, because R is small, VDD over R, or in other words, the peak current in this circuit is also extremely high. So for a small resistance, the peak current is high, but the time constant is low. On the other side, if R is very big, then the time constant is very long, but the peak current is very small. So multiplying those two together results in an equation, a value, that is independent of the actual resistance. This is why we say it's equal to C VDD squared. So this 1/2 C VDD squared switching energy is super important, and I really want everyone to really go over this derivation very carefully, make sure you really truly understand it, and recognize when it happens in practical circuits, because as I mentioned, There are lots of really bright practicing engineers that I've encountered who, when we get down to the dirty details, show to me that they don't actually understand this. So please make sure that you really spend some time trying to make sure that you understand this and can identify when and where it happens. So one question along that line of thinking, and it's something that I kind of alluded to earlier, is this fundamental? Is it fundamental in the sense that when we have a capacitor, we must dissipate 1/2 CVDD squared in charging it regardless of what our circuit looks like? So the answer, as it turns out, is no. So it is the result of a stepped voltage source. Okay, so it's just a figment of the way that we are doing the charging. In fact, what we're going to do is we will discuss a technique called adiabatic charging later. It's a technique that actually gets us below this 1/2 CVDD squared limit. So with that said, in almost all practical cases, this 1/2 CVDD squared energy is critically, I'll underline that, critically important for most digital circuits. And frankly, anywhere that you have an analog circuit or an RF circuit that happens to have some switching happening somewhere, which is more and more popular these days, then this also happens in those circuits too, unless you do something intentionally different. So before moving on, I want to do one more derivation, and what I want to do is I want to compute the energy taken from the supply. So far what we did previously is we computed the energy dissipated in the resistor. What I'd like to do now is compute the energy taken from the supply. So the energy to charge the output from 0 to 1. So we can compute this as an integral. It's 0 to infinity of VDD times I of t dt. Now I'm not actually going to do the derivation here. You can go ahead and do the integrals yourself if you like. But what you'll find is that the energy taken from the supply is equal to C VDD squared. All right, this is also super important. So I'm going to box and double underline. So if the energy taken from the supply is C VDD squared, and the energy dissipated in the resistor is 1/2 CVDD squared, then we ought to be able to compute the energy stored in the capacitor. So this should be equal to the energy taken from the supply minus the dissipated energy in the capacitor. There's nowhere else this energy could have gone. It must be stored on the capacitor. And if we do the calculation, we get 1/2 CVDD squared. And that lines up with what physics say is the amount of energy stored on a capacitor. Okay, so what this means is life is good. We've done the right thing here. We've done our calculation correctly. Our results are lining up with the fundamental physics. So before leaving this section of the lecture, I want to just make sure we understand why the circuit model I showed earlier is a good circuit model. Now specifically, it's a good circuit model because this is analogous to CMOS charging. And what I mean by that is, remember the case where we have an inverter, looks something like this. And let's say that we've connected, we were at VDD at the input, and now we've just connected it to ground. Okay, and so we have some sort of capacitor on the output here. This is capacitor C. And we just disconnected this NMOS transistor, and therefore the PMOS transistor is now charging the capacitor with a current I of t. This is directly analogous to what we were looking at earlier. Okay, so that's the analogous situation for CMOS charging. And actually, I'm just going to move this charging text down here. So what about for discharging? So when we are discharging, we have our inverter again, something like this. And in this case, we are going to connect the input to VDD. The output is some capacitor C. And in this case, we now have cut off that transistor, and we're taking the charge stored in capacitor C and discharging it to ground through the NMOS transistor. Okay, so here we say that E stored in the capacitor C is dissipated over R on of the NMOS transistor. So as a result, thus, we say that 0 switching energy is taken from the supply. So therefore, we say that the energy to go from 0 to 1 and then back to 0 is just equal to C VDD squared. So in other words, once we've charged that output capacitor to the value of VDD, once we have to discharge it, it's not like we have to take energy from the supply in order to discharge it. We just discharge it. There's no extra energy coming from the supply. So as a result, the discharging phase doesn't add any additional energy taking out, and therefore is not included in the calculation. And so the energy to go from 0 to 1 and then back down to 0 is simply just C VDD squared. So this is the bottom line for switching energy. So far what we've done is we've discussed the switching energy of a single event of charging a single capacitor from 0 to VDD and then back down to 0. But what we're often interested in digital circuits is not necessarily the energy consumed for charging one capacitor up, but we're usually concerned about the overall power consumption of the entire circuit. And the specific keyword there is power consumption. So what I want to now discuss is switching power. All right, so what we did there is we computed switching energy, but to compute switching power, what we do is we assume, or assuming a switching frequency, so our digital circuit is switching at some frequency, FSW is equal to 1 over TSW, where TSW is the period of switching. Then what we can do is we can compute an average power. P average is equal to the energy dissipated over a switching cycle divided by the period of that switching cycle. Now this will specifically be, we assume that we charge from 0 to 1 and then perhaps back down to 0 in that one cycle, TSW. So this is equal to C VDD squared over TSW, or in other words, C VDD squared times the switching frequency. Okay, so this is the basic definition of switching power in a digital circuit. Now, this is assuming that we are looking at one node and we're looking at the capacitance of one node switching up and down between 1 and 0 with some specific frequency. Now, that's a little bit of a limiting use case here. In general, however, not every node in a digital circuit switches every time or every, let's say, clock cycle. We haven't technically discussed what clock cycles mean and so on, but I think you get the point here. So in other words, every single node in our digital circuit is not necessarily switching up and down with the same frequency. So not every node switches at every clock cycle, i.e. not at 100% duty cycle. So it's not like every single node is switching every single clock period. So just to put that as an example here, let me just draw a little timing diagram. Let's imagine that we have a clock signal. It looks something like this. And the clock signal is the exception to this rule. It does switch every single period, so we'll call this the clock signal. And then let's say we have some input A, and it switches maybe something, oops, let me try drawing that again. It switches, I guess there's technically a little bit of a delay here, switches something like this. You know, not every cycle, it depends on what's going on with the data and so on. So we say that there's a little bit of a delay after the rising edge of the clock cycle, which we'll understand when we talk about sequential circuits. So what I'd like to do is define a parameter called alpha. This is called the activity factor, which means it is effectively the probability of a 0 to 1 transition during a clock cycle. By definition, the probability or the alpha for the clock signal is by definition equal to 1. And so what we can do here is we can say, you know, for this node in the circuit, we say it has some average probability of a 0 to 1 transition, and therefore it has some average probability of dissipating energy. And so we say the average power consumption is just alpha times C VDD squared times F. So that would be for one node in the circuit. If we wanted to do this for more nodes, then we need to sum up the capacitance across all of these nodes and then multiply by, for example, the average activity factor amongst all of those nodes. If we wanted to be more precise, then we would compute the activity factor of each node individually and then multiply by the individual capacitance on all of those nodes and then sum up all of these results together. So this is our definition for switching power. So given this definition of switching power, what are some ways we can do as digital designers to reduce switching power? Well, we don't have that many variables in that equation, and so let's kind of explore basically every one of them. So one way that we could reduce switching power is to lower capacitance. Now, the only real way to do this is effectively to, you know, size your gates as small as possible. And if you've already done that, then move to a new technology. So for example, if we were at 45 nanometer CMOS, perhaps we should move to 32 nanometer CMOS. Smaller devices, that will definitely make the capacitance smaller. Now, the perhaps more powerful knob that we actually do have at our disposal as digital designers is to reduce VDD. And if we reduce VDD, we're probably also going to have to reduce the clock frequency as well. All right. So reducing VDD specifically, unfortunately, also reduces performance. So we reduce VDD. That means V in on our digital gates will be lower than it was before, which means we are less strongly in the above threshold regime, which means we're going to have less current flowing through our devices, which means the resistance of said devices will be larger, and therefore the RC time constants of our devices will be larger, and meaning slower. So if we do this, we have to make this up somehow. So to make up, we typically have to make this up somehow, I should say. To make up, we can use larger devices. Well, that doesn't work very well because then that, increases more capacitance, which we don't like. Or we can use techniques like parallelism. So for example, multicore. So this was largely the solution that the semiconductor industry used when they were hitting their performance limits, for example, with the Intel Pentium 4 processors. They were trying to clock them so fast that the power density was getting so high that it was just unacceptable. And so in order to further improve computing performance, they decided to slow things down a little bit, but put in multiple cores to do processing at the same time and spread out the heat dissipation. So parallelism does help. I should also mention here that parallelism doesn't come for free. We are putting more devices there, so it also does require more capacitance. So there's no total free lunch here, but in the end, it turns out to be a worthwhile trade-off. Now, the only other term that we have access to in the switching power equation is the activity factor. So is there anything we can do to reduce activity factor? So it turns out there is. One example technique is called clock gating. So what this means is we only enable the clock when necessary. All right, so let's just draw a little circuit to emphasize what we mean by that. Now, we haven't discussed sequential circuits yet, but let's just imagine we have an array of what we call flip-flops or registers, and they're all connected together. Maybe this is some sort of FIFO queue or something like this. Now, normally, we have to route the clock to every single one of these flip-flops in this register array. Okay. As you recall, the activity factor for the clock is by definition equal to 1, which is the worst case possibility here. But let's imagine we don't always need to clock this shift register. Let's imagine this is a FIFO queue and we only need to clock it when we have data coming in or out or something like this. So what we can do is something like this. This turns out to not be the best way to do it, but let's imagine we have clock at the input of an AND gate and some sort of enable signal. Okay, so you'll recall the activity factor for clock is equal to 1, but the activity factor for enable is way, way less than 1. Okay, we only enable this circuit for a short period of time, and when we're done with it, then we gate the clock. Okay, so as a result, the activity factor on this node here, which is our gated clock node, activity factor here is much less than 1. It now depends on the probability of the enable signal going high. Okay, so with all that being said, I do want to mention that note, there are better ways to do this. Which we will discuss later on in this course. So we don't typically just want to gate it with an AND gate. We typically want to build some sort of latch type of structure that helps us reduce glitches and so on. All right, so now I want to analyze a trade-off that's quite an interesting one, and one that we need to spend a little bit of time thinking about. And specifically, that is the energy delay trade-off with VDD. Okay, so we've already kind of intuitively described why we think delay should trade off with VDD, and now we should have a pretty good idea of why energy also trades off with VDD. So I'm going to draw a plot, and I'm going to intentionally not label the y-axis. The x-axis will be VDD, but I'm not going to label the y-axis. Now, I give students a hard time when they do this, but there's a very good reason why I'm doing this. I'm plotting two different units on the same y-axis here. So we know, we've just studied that as we increase VDD, we get a quadratic increase in energy. Okay, so this is one of the y-axes. Specifically, it's proportional to VDD squared. All right. Now, likewise, when we increase VDD, our delay goes down, and that's simply because we have a larger VGS across our device. Therefore, we can invert the device more strongly, it can sink more current, and therefore its effective resistance will be lower, and therefore the effective RC time constant will be shorter. So we say we have an opposite trade-off with respect to delay. Now specifically, delay is proportional to something like 1 over VDD to the power of x, where x depends on the region of operation. So let's just write that maybe here. So depends on region of operation. So it depends if it's subthreshold or above threshold. It actually also depends on the process technology and so on and so forth. So whenever you see a plot like this, you have one curve going in one direction and another curve going in the other direction, there's typically some sort of trade-off or optimal point that we can imagine being here. Okay, so what I'd like to do is I would like to plot the EDP. This is called the energy delay product. Okay, and basically it just literally means energy times delay. Okay, and so if we plot that on this plot here, you get a curve that looks something like this. All right, now we should have a minimum, if I've drawn my plot accurately, where these two curves intersect. Okay, and so we're going to call this VDD comma opt. Now, this means the optimal VDD for the purposes solely of energy delay product, not necessarily for any other optimization metric that we may be encountering. And in fact, we will see a very similar curve to this on energy per clock cycle when we include the effects of leakage power. It's very different from this plot, so please don't get those two confused. So let's just add a little bit of text here. In general, we want to minimize energy, but not at the expense of significant increase in delay. Okay, so thus EDP may be a good metric for us to use. Some sort of figure of merit of our digital circuit is energy delay product. If we have a reasonably good, if we have a low energy delay product, then that means we're, some reasonably good point in terms of balancing the needs between energy and delay. Now, if we're looking for the minimum energy point, as we'll describe, that is at a very different supply voltage. So if we go ahead and compute what VDD optimal should be, there's a way to derive this. You can check the books for this if you like. It's approximately equal to 3/2 threshold voltage plus VD sat over 2. I believe it's the Rabai Chandrakos and Nikolic book that describes this correctly. And if you go ahead and compute this, it's around something like 0.7 volts for modern, or perhaps in this case semi-modern processes. Okay, so I do want to make one asterisk note here, because you will see a plot that looks somewhat similar to this later. This does not take into account leakage power. So as it turns out, that energy curve, that's only considering switching energy. It does not include any aspects of leakage power. And as it turns out, because when we scale VDD lower, leakage power actually decreases, but the delay increases, and it increases a lot, especially when we get into the subthreshold regime. Delay increases exponentially. And although leakage power is decreasing, leakage energy per clock cycle actually increases because the clock period must decrease exponentially, and therefore we're integrating more leakage power over an exponentially longer amount of time, and that results in a lot more energy. Okay, so in reality, and let me just draw this in here, in reality this goes here if we include the effects of leakage. Okay, so there's another minimum energy point that happens when we balance dynamic power, switching power, with leakage power. So if we have time, we'll get to talk about that later in this course. So while we're on the topic of dynamic power, I want to take a brief amount of time and discuss a technique to actually get below this 1/2 C VDD squared limit. Now this is specifically referring to adiabatic techniques. Getting below CV squared. Okay, so the main reason we have this CV squared energy is because we're using a stepped voltage source. So the idea behind adiabatic approaches is, instead of a stepped voltage source that is used to charge our capacitors through an RC network, why don't we try something different? Try a slow ramp, set specifically such that the ramp voltage, or the voltage across the voltage source that's creating this ramp, is just above V out by a small fixed amount. Okay, so what does this mean? This sounds kind of weird. All right, so the idea here is let's draw a circuit to give us a better idea of what we mean here. So we have some voltage source going into a resistor and then into a capacitor. All right, just like we've always done. Now in this case, we're going to start this voltage at 0, and instead of instantly going up to VDD, we're going to have a slow ramp, and then finally we'll be at VDD. Okay, so this is called V ramp, and specifically I want to call out the ramp time here. This unit of time here is called T sub R. All right, this is resistor R, this is the capacitor C, and this is node V out. As we do this, we are still going to get some current I of T that's going to charge this capacitor to V out. All right, so we can say, based on this above definition, that I of T is equal to V ramp of t minus V out of t divided by R. Okay, so we're doing this and to set this to some constant value, let's call it equal to capital I. Okay, so let's go ahead and just draw the plots of what this might look like. Actually, I'm going to make this a little thinner. The current plot is rather simple. So we're saying the current is fixed while the circuit is charging. Okay, so let's just go ahead and plot the charging behavior here. So we're saying the current is fixed. It's at some value here. If we have a fixed current charging a capacitor, then that makes a ramp, right? And then once this voltage hits VDD, I suppose I should label this axis. This is V out of t here. Once this hits VDD, then we're done charging. We set the current to 0, and the voltage just holds. Okay, so in other words, rather than doing an exponentially decaying response that converges to the value of VDD, we instead do this through a ramp. Now, specifically, we indicate that the time here to do this is time t sub r. So let's go ahead and write the equations here. We say that V out of t is equal to 1 over c times the integral from 0 to t of I of tau d tau. Now, because I is a constant, we can say that this is equal to IT over c. Okay, so we set t sub r such that V out at t sub r is equal to VDD, which is equal to ITR over C. So in other words, we want to set I to be equal to C times VDD over TR. Okay, so this is the fixed current that we are delivering here. Let's just label that on the plot. So this is equal to C VDD over TR. That's our, this is equal to I. Okay, so what does that give us? Well, we can now go ahead and compute the energy dissipated in this circuit. This is equal to the integral 0 to TR P of t dt. Okay, we're only dissipating energy during the charging cycle, so we can integrate from 0t to tr. Of course, we could integrate to infinity in this example, but anything after time tr is just 0, so we can just set the limits of integration to 0 to tr. So this is equal to 0 to tr I squared r times dt, which is equal to C VDD over TR all squared times R times TR, right? So this is equal to RC over TR times C VDD squared. Okay, so we're seeing this C VDD squared thing pop up here, but now it's modulated by RC over TR. All right, so the conclusion here is that if I'm going to write this in a different color here. If TR is larger than 2RC, then E dissipated is less than 1/2 C VDD squared. Okay, so that's really cool. So basically what this is saying is that if we slow down our ramp away from the natural time constant of the natural RC time constant of the circuit, if we intentionally charge the circuit slower than the natural RC time constant of the circuit, then we could potentially have lower than 1/2 C VDD squared dissipation in our circuit. In fact, the limit as we take TR to infinity, if we charge infinitely slowly, of this formula, RC over TR times C VDD squared, is equal to 0. So that's really interesting, right? So if we charge infinitely slowly, then we dissipate 0 power, ideally. Okay, so, or we consume 0 energy. So this is really interesting. That means if we operate very slowly, then we could potentially be exceedingly energy efficient. This is a very attractive idea to a number of designers. You know, oh, I can build a whole digital system that consumes no power. Now, this is a curious possibility here. In practice, it turns out to be rather difficult to do this effectively without overhead in order to generate these ramps and so on. And then there's all sorts of interesting, how do you build timing for adiabatic logic and so on. Many researchers have tried this, and the conclusion is that it's really hard to build a truly adiabatic logic family that has significantly improved performance over voltage-scaled static complementary CMOS. Now, with that said, there are some interesting applications where this is possible to do, and we can indeed get significant energy savings. This is particularly true, for example, for clock driver networks, which don't have logic associated with them. They just generate square waves to clock flip-flops and so on. And in fact, my own research group has published work in this area that has shown that we can indeed save significant clock power through some adiabatic approaches. So as I mentioned, adiabatic techniques are really interesting, but unfortunately, this is exceedingly difficult to implement in practice. The most common approach, I would say, is what we call a stepwise driver. So the challenge in building these adiabatic waveforms is we need this smooth ramp. And that's kind of an analog-y thing to build, which is not always easily compatible with most digital systems. So a simple way to do this is the following. What we do is we have a collection of PMOS transistors. Maybe a bunch of these. Okay, and we tie all of their connections here together, and then we tie the other side here to ground, okay, with an NMOS transistor. So this is voltage V1, this is voltage V2, this is Vn, this is Vn minus 1, etc. Okay, and then we have our output load CL as an example. So the idea here is if V1 through Vn are equally spaced voltage levels, then what we do is we sequentially turn on V1 through V2 all the way through Vn in a stepwise fashion. Right? So we start at 0, and then we step up to V1, then V2, V3, etc., until we hit our peak. And then we're at our valid logic level. So this is 0, this is VDD. Now between each one of these, we have what we call a hard charged or a RC step. So there is an RC time constant associated with each one of these steps. Okay, but if we make the RC time constant small, you can go through the math and you can see it's actually C delta V squared that's occurring here. That's the energy loss here. And because it's delta V squared and delta V is smaller than VDD, the net result of energy dissipated in the circuit is actually quite a bit less. So we can say that the energy dissipated, E dissipated per step is equal to 1/2 C times, in this case, it's delta V, which is VDD over N squared. Okay, so that's fantastic, right? If we break up our charging operation into n discrete steps, then we reduce our dissipated energy by a factor of n, so long as each step can individually settle prior to the start of that next step. Okay, so this is what we call, if we look at this part here, this is adiabatic charging. Now, once we're at VDD, we have a couple different options we can take here. We can take that energy in VDD and we can just dump it back to ground through that NMOS transistor, something like this. Okay, so build something like, I don't know, a staircase at the end of the first level of Super Mario World on NES. But it turns out that there's actually something smarter we can do here. Rather than do that, I'm going to erase that, we can actually go ahead and step down. Now this should be technically drawn symmetric to the other side there. I probably don't have that totally correct here. But we could do something like this. And what this does is a process called charge recycling. What we mean here is rather than take all of the energy stored on CL and just, it's CV squared, and just dump it to ground, why don't we take that energy and dump it to the supply voltage that's a little bit lower than the current voltage on that capacitor. So we recycle the charge that's been stored on the capacitor to push it back to one of those n-1 supplies. In this way, we further save additional energy. So the total energy taken from the supply, if we do adiabatic charging and charge recycling, is equal to C VDD squared over N. Or in other words, it's the conventional amount of energy divided by N. So if you have a bunch of steps, you're going to save a bunch of energy. So again, this is very, very cool, exciting way to really save energy. Now, as I mentioned, how do you generate all of these different supply voltages? Do you need N DC-DC converters? Well, probably, actually, in the basic cases, yes, you do need N DC-DC converters, which adds significant overhead to your circuit. How do you route N different power supplies to all of your circuits and so on? This is actually rather complicated. We published a paper a few years ago at the International Solid State Circuits Conference in which we developed a staircase circuit that used an internal switch capacitor driver network to automatically generate these supply rails in an efficient and very effective and low area way. That we were able to demonstrate in microprocessor kind of loads that we could reduce clock power by around 50% or so. And this was with a small handful of steps. So that was actually quite exciting of a result. Now, the other thing that, that you have to think about here, you are intentionally slowing down the edge rates. So as a result, your edges here are slower. That means you must operate your circuits to be slower. And that is a major downside of this approach. Okay, so please do keep that in mind. Adiabatic circuits, by their very nature, must be slower than non-adiabatic circuits. So that is definitely a trade-off that comes into play here. One other thing I'd like to mention is that adiabatic approaches are not only useful for digital circuits, but basically anytime you need to charge a capacitor efficiently. So this could be true, for example, in neural stimulation circuits. My research group has indeed published papers on doing adiabatic charging of neural stimulation electrodes, which happen to be primarily capacitive. And this could also be true for charging of any other kind of capacitive load, as there are many other applications for this. So the last item I want to talk about in this lecture is short circuit current, or short circuit power. And I guess we'll specifically refer to this as short circuit dynamic power. Not to be confused with dynamic switching power, but this is short circuit power. And we say dynamic there because it doesn't happen continuously, but only over a short period of time. So let's draw our basic inverter structure here. Something like this, NMOS, PMOS transistors. Oops, not PMOS on the bottom, NMOS on the bottom. Okay, now let's imagine this is our input and that's our output. So let's imagine that V in is not a perfectly straight signal, but some sort of ramp signal. So this looks like V in, okay? And so what we say here, and well, I guess I should specify this goes between 0 and VDD. Perhaps that's obvious, but let's just make that extra clear. So there's a region in the middle here, depending on what VDD is, but for most standard CMOS supply voltages, there's a region where both devices are on, both NMOS and PMOS are on and saturated. So when the input is around mid-rail, we have both of them on and both of them are saturated. Now this does depend on VDD. If VDD is very low, perhaps they never actually turn on, everything's operating in sub-threshold, but I think you get the idea. So let's just make a note here. So normally we have some sort of model of our output load capacitance here. And because that load capacitance is finite, that means that if we have a ramp at the input, even if we had a perfectly straight line at the input, we're still going to get a ramp-like signal at the output, where this is VDD and this is ground or 0. Okay, now leave a little bit of space in between the inverter and CL. I'm going to add another element there shortly. Okay, so what I want to first do is I want to plot V in versus time. Okay, so this is V in, and let's say we start V in at VDD, and then we ramp down, and we're down for a little while, and then we ramp back up, and then we're back up at VDD. Okay, so let's just imagine this is a normal V in kind of waveform. What I want to plot next is what happens to a current branch going straight from the PMOS through the NMOS. We'll call this I short circuit. Okay, so I want to plot I short circuit. Oops. This is not current that is being used to charge the load, but rather it is current that is being just shunted between the PMOS transistor and down through that NMOS transistor. So if we look at kind of the center region here, what we're going to get is right when, assuming we have an inverter that's been sized for equal pull-up and pull-down strength, we're going to get a peak short circuit current, I peak, and then it's going to kind of decay around that, something like this. It should be symmetric. My drawing is not super good here, but I think you get the idea. Now the same thing can be true over here. We have the same peak, and the current, looks something like that. Okay, that's slightly more symmetric. In fact, I'm just going to redraw this first one here because that was awful. Something like that. Okay. So what we can further say is how do we model this? Okay. So what I'm going to do, oops, I don't know why that didn't work, is I'm going to approximate this as this shape as a triangle. It's not obviously a perfect triangle, but I think it's a reasonably good triangle. And specifically, the base of the triangle is T short circuit. Okay, so if we approximate this as a triangle, then what we can do is we can compute the energy, the short circuit energy consumed in one of these iterations. And it's just effectively the area of the triangle, right? It's 1/2 T short circuit times VDD times I peak. And there's 2 of these per cycle, so that's times 2. Okay. And so therefore the short circuit power, P short circuit, is equal to T short circuit times VDD times I peak times F, where F is the switching frequency. Now this is kind of an inconvenient formula. It doesn't really follow the other formulas that we tend to use. So what we're going to do is we're going to say it's actually something like C short circuit, which we haven't defined yet, times VDD squared times F. You can say, well, how the heck did we get there? Well, basically what we do is we say that this C short circuit is not a physical capacitor, it's just a model. Just a model. Okay, and so basically what we do is in our circuit here, we attach an effective capacitor to ground called C short circuit, and we effectively translate the value of C short circuit into the actual P short circuit formula here in order to get an approximation of what this value is. So this is kind of a weird heuristic, but it just allows us to basically lump it in to the calculation of dynamic switching power as opposed to having to do a whole new computation of short circuit power. So now that we understand what short circuit power is, the natural next question is, well, how do we reduce it? How do we minimize its impact? So how do we reducing short circuit power? It turns out we don't have a whole lot of control here, but let's discuss two different options here. Option one. So what do we have at our disposal? We can't really change what the input looks like. The input is what it is. So we can change the output perhaps by using a very small load capacitance. Let's say somehow that's possible. Okay. So if we were to do that, V in has some sort of ramping waveform that looks, whatever it looks like, something like that. And V out, then if it has a very small capacitance, it's actually going to have a very sharp transition here. The fall time is going to be very sharp. Okay, so it turns out that this is probably not a good idea because what ends up happening is that basically if the output switches very fast, then at the point where the input is at its halfway point, the output also happens to be near its halfway point as well. And so this means the two transistors are definitely on in saturation, and the current that flows through them is actually the maximum possible current. So this actually results in a maximum short circuit current output here. Okay, so this is not a good solution. So if using a small load capacitance was not good, why don't we try the opposite? Why don't we try a large load capacitance? Okay, so let's look into this again. So let's say Vn is our usual ramp here. Ramps up something like this. Okay. Now V out, if we use a large load capacitance, then what it means is it's going to ramp down very slowly because it has a lot of capacitance to discharge. Okay. So from this perspective, when V in crosses the 50% point, we see that V out is basically still at VDD because that output capacitance is so big, which means that one of the transistors is going to be deeply in the linear region while the other's in the saturation region. So there's not actually going to be a lot of short circuit current. So we say here that I short circuit is approximately equal to 0. So the answer to does this work is yes, it does work. However, there's a big problem here. So let's write down what that problem is. However, it is not possible in normal cascaded logic to make slow output ramps because if you have a slow output ramp, then the output of that gate will then be the input to the next gate, and that means the next gate would have to have an even slower output ramp and so on and so forth. Okay, and so it just cascades down the chain where you start with a really fast gate and then you end up with slower and slower and slower gates. All right, this is not how we want to do design. We don't want slow gates. Okay, so in practice, it's usually best to design for small capacitance, even though this does result in the worst case output short circuit current. So we want to design with slow capacitance, specifically with equal rise and fall times. Now, if you follow this practice, in this case, P short circuit will be about less than 10% of P total. Okay, so if you follow the practice and you have good equal rise and fall times, then it turns out P short circuit isn't a huge deal. We have much larger contributions from dynamic switching power, as an example, than we get from short circuit power. So that would be my recommendation. Don't try and play games with making output ramps longer and so on. Just keep things simple. Keep the rise and fall times as equal as possible. Make the capacitance as small as possible, which helps with dynamic power and frankly also helps with speed. And this is kind of the best way in general to do digital logic design.